Log on, tune in, find out. Another good idea from Cambridge.
Talk about reduction of order for discrete systems.
Okay, so this is the title of my talk, Reduction of Order for Discrete Systems. Of course, the kind of systems I'm going to deal with are not any kind of discrete system, but systems of a certain form. So the work I'm going to present is work with Andrew Pickering, and what I'm going to give you first is the motivation for doing this work. So for several years now we were interested in building an approach of deriving hierarchies, integrable hierarchies of in principle partial differential equation in 2 + 1 dimension, and then taking reduction, simple reduction to partial differential equation in 1 + 1 dimension to ordinary differential equation, and then moving to the discrete case, starting from a certain class of equation, going to from 2 + 1 to 1 + 1, and also to differential delay and to discrete equation. I will explain in a moment which kind of equation we are dealing with. So we were deriving all these kind of hierarchies of differential equation together with the linear problems, and for that reason we were interested in using them to derive the hierarchies, what I'm going to be talking today, of ordinary differential equation and discrete equation that we derive with the linear problems, but I'm not going to be talking about the linear problems now. So the point is that, of course, because they were arriving at the ODE and discrete case from integrable hierarchies, we were expecting them to be of Pine-Levé type, so Pine-Levé hierarchies, but sometimes it's easy to identify them, sometimes it's not that easy to really identify it. So normally what you need is to reduce the order not only of a single system but of all the hierarchy. And because a reduction of order is needed, what we thought of is of using properties which are typical of the completely integrable partial differential equation or lattices equation from which they arrive from. So this is the idea, and this is the method we were developing in the continuous case. And then what I'm going to talk more today is the extension to the discrete case. So how to reduce the order, how to sum or integrate, whatever you want to call it, these discrete hierarchies. And I'm going to present, well, really 2 or 3 of them, which are discrete Pine-Levé hierarchies, in the sense that the first member of this hierarchy is a discrete Pine-Levé equation. So this is the outline of my talk. First, I'm going to give an introduction of the continuous case. I'm sorry for some people in the audience that might have heard the approach in the continuous case, and in any case what I'm going to say in the continuous case is very simple, so everybody's going to find it really very simple, but it's the idea we are following. So that's why I want to explain it for the KDB case and for Pine-Levé 2 and Pine-Levé 34. So this is the introduction. Then I'm going to be talking about the extension of the method to the discrete cases, which are the difference with the continuous case, and then how we identify some discrete Pine-Levé hierarchies. And I'm going to give a couple of examples, one that arrives from as a reduction of a Toda hierarchy, and the other one that arrives from Volterra hierarchy, and then, well, I'll mention the conclusion. So as I say, this is the introduction, looks exactly as what Emma Previato was saying in one of the slides. So I mean, something very well known for everybody. So I start with the KDB equation here, and it has a similarity scaling reduction that yields this third order equation. This equation can be integrated. I think I'm going to use the equation can be integrated once and gives the P34 equation in the INS classification. That's why I'm calling it like this. And of course, they represent the same function, but is better defined as a second order than as a third order. So we know that using the Miura transformation that relates KDB and modified KDB, P34 is related to the second Pine-Levé equation in here in the big U variable via the Backlund transformation, so which is the combination of these two equations together with the shift on with this connection in the parameters. So if we eliminate one or the other variable, we obtain one or the other. So this is the simple example, and I'm going to carry on with the example. Why? Because I take this equation here, the one of third order, and I write it like this as B acting on this quantity, where B is one of the Hamiltonian operators of the KDB hierarchy. So I want to think of this reduction of order of the second order equation in a slightly different way. So I write it like this. So I have the Miura map under which the Hamiltonian operator factorizes in this way, where beta tilde is the Hamiltonian operator of the modified KDB hierarchy, which is very simple. And this is the fresh set derivative of the Miura map. So all these are properties of the PDEs where they come from. And then, because I write the equation like this, I use the factorization, and then I go back to the ODE case, and I have the starting point. Using the factorization, I have this, or written explicitly like this, and I can integrate this modified equation because it's a straight away where alpha is a constant of integration. And this equation, which is the integration of the modified system, is Pine-Levé 2. So what we have done is we have started with this equation, which is written in this form. That's why I was saying at the beginning that I'm talking about reduction of order of certain systems. So we start with this. We use the Miura transformation and the factorization. We have the modified system that we can integrate easily because of this form. Well, this is the derivative I didn't say, but derivative with respect to x. So we integrate. We have P2. And then how do we relate this equation with the integration of this one, which is what we wanted, that we know in this case, of course, but it's what we want in general. So we take this equation here, we write it here, but using the Miura again, and what we build is with this one and the Miura, we have a Backlund transformation between this integrated modified system and this other one, which can be obtained from here, which is the one we know from the beginning, but it's the way I'm thinking of it. So I start with this one. I use the Miura and the factorization. I integrate, I modify, integrate it, construct the Backlund transformation between them, and this is the integrated and modified system. So this is the idea again. The equation, I modify, I integrate the modified equation, I get a second Pine-Levé equation, I construct a BT between P2 and P34, and then here I have the integration of the system of my starting point. So what's the advantage of doing this? Again, for this particular example, there is no real advantage, but if you think of what I'm saying, the advantage is that this integration is much easier, much simpler than the one in here. And what's the idea I'm using? The idea is that I'm using properties, so Mura maps and Hamiltonian structure of the integrable system, completely integrable system of partial differential equation for the ODEs that we obtain in the reduction to reduce the order. And in this way, what we have been able to do is to identify some Pine-Levé hierarchies, which is what I'm going to talk now. Something I would like to mention now is that because the only thing I have used in all this is that I need some Hamiltonian operator acting on something. I haven't used at all this something, what it is. I can reduce the order of systems which are not integrable, because the only thing I need is to have Hamiltonian operators acting on whatever thing in principle. But of course, when I'm looking for Pine-Levé hierarchies, I want special forms of this thing here, which are the Hamiltonian densities, of course. So again, in the continuous case, and this is the idea that was in the continuous case, what we have is equation of this form, where B is a Hamiltonian operator. We have Mura transformation. I'm talking here about systems of n variables. So little u are the unmodified variables, capital U are the modified variables. So I have Mura transformation, factorization, where this B tilde, which is the Hamiltonian operator of the modified system, is we take system where it is of this form. Then this is the integrated modified system, where gamma is the constant of integration, which is an n vector in general, n constant vector. And then what we have is the BT, which is these two equations. One of them is the Mura map. The other one is the modified system here, but written combining both variables. And what it here is the Backlund transformation, and then here is the Backlund transformation. It defines, it relates to systems. This one is the integrated modified one, and this one, which is just substituting the solution for U from here in the Mura, gives the integration of the original one. So this is the idea in the continuous case. Oh, sorry. So now I'm going to the discrete case, and I'm going to say which is the kind. I mean, very briefly. Sorry, I have a kind of difference with the notation here in the next two slides with the ends. But anyway, so the kind of equation we are dealing with are this one here, which is a 2+1 integrable system in one discrete variable, two continuous variables. R is the recursion operator of a lattice hierarchy. So for example, it's going to be the Toda and the Volterra later when I talk about. So I have these terms here that contains the Y dependence. Then I have the standard flows in 1+1 dimension, and then I have here some non-isospectral terms. So this kind of systems, also in the continuous case where we start from for the reduction, are non-isospectral, and this term, which enter in the non-isospectral condition of the linear problem, are important in the reduction to get the Pine-Levé, because they give the non-autonomous terms, in the discrete and in the continuous case. So for example, I'll say just briefly, this is in the Volterra case. This is the system we have. I will be back later to this. So here is the y dependence, the standard flows, and this beta. That's why I'm saying they enter in the linear problem in the non-isospectral condition is the part that gives the non-autonomous term. So these were the kind of equations, the kind of system we have, and these were the kind of reduction we obtained. And what I'm interested in now is to talk about this, about going to the discrete level. So for some choice of the beta, we have this, so we choose only to keep the local terms, and in the first non-trivial case for this hierarchy we have m equals to 2, and we get this equation after integrating once. This omega 2 is the constant of integration, and we looked at the moment I'm not talking about the integration, I'm only giving one example. So it can be considered two different cases. So in the case where beta 1 is equal to 0, we get the discrete pi level 1, and in the case where beta 1 is non-zero, the equation before can be reduced the order again, and what we obtain is a discrete pi level 34 that contains parity terms. And we also see that we can derive the BT between this equation and the discrete pi level 2. But this is just one of the examples we derive from our hierarchy. So because when you look at the other member, you obtain the same. So it, of course, it sums to a fourth order discrete pi level 1, and then the same for discrete pi level 34 and discrete pi level 2. So with the Backlund transformation, so we thought let's go to look at all the hierarchy and use build a method to reduce the order of the whole hierarchy. So this is what we did, is the extension of the method to the discrete case. And what I'm going to say is mainly what are the differences. So now we consider n discrete equations where Pn, n components, are the original variables. So our systems of this form, again, beta acting on some k of Pn, where beta is a Hamiltonian operator, and then we have, like as in the continuous case, we have a Mura transformation. So un now are the modified variables, and the difference with the continuous case is that in the factorization here of the Hamiltonian operator, so where we have b tilde, which is Hamiltonian operator of the modified system, and n prime dagger are the first set derivative and its adjoint. So we assume that this Hamiltonian operator for the discrete system is of this form now. So instead of being, as in the continuous case, just a constant matrix times the derivative with respect to x, and it was easy to integrate. So now we consider systems of this form where the dependence on E, I don't know if I said before, E is the shift operator. So the dependence on E is in this part D here. So D plays the role that was playing this in the continuous case. So we use the modification, we assume is of this form, and what we obtain is the sum or integrated modified system where these omega n are the constant of integration, and what we do on the way is to build the Backlund transformation that has two parts. One is this one, the Mura, and the other one is this one that comes from the integrated modified system. So we assume that we can solve linearly for the variables un, like this, and when we put this into the Miura, what we obtain is the sum of the original system. So the idea is the same. We have a system that we want to reduce the order. We have a Miura and a factorization, which allows an easy integration of this one. Then we build the Backlund transformation, and then we have the integration of the original system we had. So the reduction of order depends on the operator D, before this operator here, and I'll say what I mean later, because in the continuous case, the reduction of order is by n, being n the number of equations. In the discrete case, even when, for example, for the Volterra case, which is scalar equation, we can reduce the order by 2 by using this. So now, a couple of examples, briefly. So a TODA example where I have two component systems, which are this one, in P and Q. B here is one of the 3 Hamiltonian operators of the TODA lattice hierarchy, which is written in this way. Well, here is E that I said before, the shift operator. So we know that there is a Miura map, which is written here, where U and V are the modified variables, the variables of the modified system. Here is the factorization, where this is the Freser derivative, and the B tilde here can be written in this way. So the dependence on the shift operator is really on D. So these are the ingredients we have, and what's the result? The result is that we have been able to integrate the modified system. Omega 1 and omega 2 are the 2 arbitrary constants of integration. We have the Backlund transformation, which is composed of the Miura and this other part, which, as I said before, is exactly this, where we use the Miura. And then we have, well, this is another way of, the BT written in a different way. I wrote it like this so that you can see that we can solve linearly for the modified variables un and vn in terms of the unmodified one. This is what I do. And this is the sum unmodified system, which is just what happens when you use this u and vn and put it into the Miura. So what's the application? So the application is that this, what we have from this TODA case was a hierarchy of discrete equation we derived in a paper in 2007, which is this one, the one I'm going to consider. Q is the recursion operator of the TODA lattice, which is the quotient of the B I had before, the other Hamiltonian operator, A. And this hierarchy can be written in the form is needed. Well, yes, in terms of the Hamiltonian densities, but anyway, it can be written this way. So I use the ideas I described previously, and for example, for the first member, these are the K1 and K2, and what we obtain is this system of discrete equation, which is equivalent. We find it in the way we find the BT, the Backlund transformation, to this other system, which is the asymmetric discrete pi level 1 written in its 2-component version. So what this means really is that the hierarchy we have here can be integrated and relate through a Backlund transformation to an asymmetric discrete pi level 1 hierarchy whose first member is this one. Of course, I haven't written explicitly the hierarchy, but it can be written down very easily using the equation before. So this is one of the examples. The other one, which even if it is a one component, it's slightly more, not more complicated, but slightly different in the sense that what we have are systems of this form. It comes from a Volterra example. B and A are Hamiltonian operator of the Volterra hierarchy, and what we have in this case is the factorization. In fact, for this combination, C is an arbitrary constant for this combination of the Hamiltonian operator. So there is the Miura map, the factorization. B tilde is the Hamiltonian operator of the modified system, which is written here. So again, we have is of the form C, D, C again, and here is the part that we use for the reduction of order. So this is the D, and in this case, because it's of this form, even if it is a scalar equation, it allows a double integration, where gamma 1 and gamma 2 are the two arbitrary constants of integration. So the result in this case is again the same. So we have been able to reduce the order by 2 of the modified system. We construct the Backlund transformation, and we are able to reduce the order by 2 also of the original system. So being more explicit, the kind of discrete hierarchies we had were like this, are the recursion operator of the Volterra lattice hierarchy. We have, well, these are just the action of R on UN, etc. But what we obtain is that each member of the hierarchy has been summed twice. And what we get is that the modified hierarchy is the discrete pi level 2 hierarchy, including parity-dependent term. The integration of the hierarchy we started with is the discrete pi level 34 hierarchy, also including parity-dependent terms. And what we obtain is the Backlund transformation between both discrete hierarchies. So this is the first non-trivial example where, and this is the result. So this is the discrete P2 equation, the discrete P34, and the Backlund transformation. But what I would like to stress is that it's not that we derive this for these members. So we have the BT for all that relates both hierarchies. So, well, I'm finishing. So here are the conclusions. Just to say that what I wanted to present is a method of reduction of order that we were interested in having, because for some cases like the P2, not P2 equation, but P2 equation and P2 hierarchy and P34 hierarchy in the continuous case, it looks like maybe not necessary. But for example, in the continuous case, when we wanted to identify pi level 4 hierarchy, it wasn't so obvious, and we used this and we were able to identify a new pi level 4 hierarchy. So that's the reason why we were looking for it, for something to identify the hierarchies. And what I would like to stress two things. First is that what we are doing is using properties of the partial differential equation of the hierarchy of partial differential equation where they come from, and also that in principle it could be applied to some non-integrable systems, of course, of a certain form. Thanks.